Hi guys, hello everyone and welcome to the channel. So today in this particular video we are going to talk about linear combination of atomic orbital and their effects in the molecular orbital theory, and we are going to talk about this particular topic from the quantum mechanical point of view. Now this is also one of the topic which has been recently added in the GATE syllabus. Actually it was there but they have recently highlighted it. There are a few very basic kind of questions which are asked from this topic, so that's why I thought to include this topic in this particular series so that you don't miss out questions if they are asked from this particular topic. Alright, so I'll be explaining you some basic things about linear combination of atomic orbital, and then we'll see the quantum mechanical aspect of that, and then we'll take questions based upon that. Okay, so the video will be in two parts. In the first part I'll be just explaining you about the concept, I'll be explaining you about the basic theory of the topic, and then I'll be going for the previous year's questions, and that's how this video will end. Alright, now before telling you anything about this particular topic, let me tell you about my classes which are running right now on Unacademy Plus. So I have started two new batches for GATE and for CSIR net, both exam preparation. So if you are interested in joining those classes, you can take Unacademy Plus subscription using my referral code, that is N_Huda. So you can use that particular referral code to take Unacademy Plus subscription, and you can access my classes on Unacademy. For more details, you can contact me on the email ID provided in the description of this video. Alright, now having said that, let's continue with our video. Alright, so we will start from this particular interactive slide over here, which talks about the linear combination of atomic orbitals. So if you understand, if you have read about molecular orbital theory anywhere in your coordination chemistry or in your chemical bonding or in your quantum mechanics, like in any of the aspect, so the basic explanation or the basic definition of the molecular orbital theory says that you will be having atomic orbitals which are going to linearly combine, okay, and they are going to form molecular orbitals. Now these linear combination of atomic orbitals can be done in two ways, can be done constructively or it can be done destructively. So based upon constructive and destructive like overlapping, you will have two different types of molecular orbitals. You will have bonding molecular orbital and you will have anti-bonding molecular orbital. Now that's what the basic theory is all about. Okay, so atomic orbitals getting combined linearly. What does that linearly means? Means head to head they are going to combine. Okay, and this linear combination of these atomic orbitals give rise to the molecular orbitals, and molecular orbitals can be bonding or anti-bonding. Now if you look upon this particular diagram, so here I have made 1s orbitals. Now these two 1s orbitals which you can see over here, which are shown by the red spheres. Now red color of orbitals, wherever I will show you in this particular whole video, red color will signifies you positive lobe or the positive like side of the orbital, and blue color is going to show you the negative side. Okay, so blue color is going to show you the negative lobes, and red color is going to show you the positive lobes, wherever it will be. Now if you see here, so both these s orbitals are there. S orbitals are positively, like it has a positive electron cloud around it. Now the blue color is also there, but that is deeply buried inside, so that's why we cannot see that. So overall it looks like a spherical red color, like the positive charge like surrounding this s orbital. Now these two s orbitals, when they linearly combine, they are going to form like bonding molecular orbital and a anti-bonding molecular orbital. Now this bonding molecular orbital is done when there is a addition of these two wave functions. Now let's talk about it from the like quantum mechanical point of view. So let's say I have expressed it as wave function psi1s, and this is also psi1s. Okay, so for just to make sure that you can differentiate between both of them, let me put a dash over here. So this is psi1s and this is psi1s dash. Now these are the two wave function of two atoms having 1s orbital. Now when they are going to combine, they can combine as psi1s plus psi1s psi dash 1s. Okay, so that means both of them have combined constructively over here. Now when they form constructive overlapping or constructive combination, they are going to give a bonding molecular orbital because its energy will be lower. Now the other one which we will be having will be psi1s minus psi dash 1s. Now in this case they are going to form anti-bonding molecular orbital. Now how does the wave function is going to look like? So if the wave function like representing your 1s orbital is like this, and the wave function representing this particular 1s orbital is like this. So their constructive overlapping is going to form a wave function which is shown with this particular red colored wave. Okay, so this is how the bonding molecular orbital wave function is going to look like, and for anti-bonding molecular orbital you can see that the wave function is going to be something like this, having a positive side and a negative side. Now if you look upon the visual diagram of it, it shows something like this. In the constructive overlapping you have this whole surface like having similar charge. So the electron cloud is basically surrounded by the whole, like it's surrounded in the oval shape, and these two dots are just like the foci of the ellipse. So these two dots are basically showing you the two atoms. Now here these two dots are obviously at their own positions, but here the orbitals have destructively overlapped, so that's why this particular one is 1s and this is 1s dash in the destructive manner, that is minus 1s dash. And in the center of that, so this is positively charged, this is negatively charged. In the center of them there will be a place, or there will be a plane where there is no probability of finding electron. So that particular plane is called as your nodal surface. Okay, that is going to be nodal surface or nodal plane or nodal point. Okay, so there are many definitions of it depending upon what you are talking about, whether you are talking about a line, whether you are talking about a plane or a surface. So this nodal can be decided like that. So remember one thing, I just want to give you some definitions over here. First of all, what is orbital? Okay, what is an orbital according to quantum mechanics? So orbital is a radial extent around an atom up till which probability of finding electron is there. Okay, so that's what an orbital is. So let me just write it down here, that the space, okay, the space around an atom where probability of finding an electron is, okay, where probability of finding an electron is is present, okay, or basically there is some probability of finding an electron in that particular space, or that particular radial extent. This is space you can also write down as radial extent. Okay, so this particular thing is called as your orbital. So orbital is nothing but it is telling you that up till where or up till what surface there is a probability of finding an electron. So these shaded regions are basically showing you that up till which region or up till what extent you can find an electron. That's what it is all about. Okay, now once you have understood this particular thing, now you can understand for the p orbital like forming bonding and anti-bonding orbitals. So let me show you that as well. So let's say the pz orbitals. So pz orbitals are going to form the sigma bonding. Why? Because they do head-on-head collision or head-on-head overlapping. So basically pz orbitals form sigma bonds. You should know that thing. Okay, and here also these bonds which are formed will be your sigma bond only. Okay, so this is sigma bond and sigma anti-bonding. Now if I write down if I write down the parity, or if I write down the symmetry of these orbitals, so sigma, this bonding orbital has a G-rate parity, and sigma anti-bonding orbital has un-G-rate parity, because there is no inversion center here, whereas here you have an inversion center. Now talking about your pz orbitals, so here again these are two pz orbitals. When they are going to combine, they are going to combine in two ways. They are going to combine constructively and they are going to combine destructively. So if this is represented by psi like 2p z, and this is like psi dash 2p z, so here the wave function will be represented as psi 2p z plus psi dash 2p z. Okay, and this one is going to be represented as psi 2p z minus psi dash 2p z. Okay, so this is going to be the wave function representation of these two wave functions. Now if you see this is a constructive overlapping, this is destructive. So this is going to form a bonding molecular orbital, this is going to form a anti-bonding molecular orbital, the same way how we have seen for the s orbital. But here again you can see that since there is a inversion center in the whole thing, so the parity will be G-rayed. So I can write down G here. Here there is no parity, okay, because there is no inversion center present, so that's why you can write down un-G-rayed here. So this is going to be like sigma G pz sigma star u pz. Okay, and this particular dotted line is again showing you the nodal surface. Okay, so simple thing it is. Always whenever there will be a overlapping of atomic orbital, you are going to get bonding orbital, anti-bonding orbitals based upon how the wave functions have overlapped, and that's what is all about linear combination. Let's understand about the pi bonds. So the pi bond can be formed by the linear combinations of your px orbital and of the py orbital. Let's say the px orbital is the one which I have shown here. Py will also do the same thing. So even the px orbitals are going to form your bonding molecular orbital. So in that particular case, that means when they are going to do the constructive overlapping, okay, in that particular case, the wave function which you are going to get is going to be like something like this. Okay, so this is the constructive overlapping. The positive lobe are going to overlap on each other, the negative lobes are going to overlap on each other, so forming a positive cloud and a negative cloud above and below the atom. So these dots are showing those atoms. Okay, now if you see, this will be called as pi bonding molecular orbital. The parity of this will be ungyred because there is no inversion center obviously here. Now if they do the destructive overlapping, okay, if they do the destructive overlapping in that particular case, now what is going to happen, that these orbitals are going to get repelled away from each other, forming a nodal plane in this case. Okay, this is the nodal surface which we are going to get, and this particular one will be pi anti-bonding orbital. Now what is going to be the parity? Since you can see there is an inversion center, there is a point of symmetry in this case, so that's why it will have gerade as the inversion, as the parity or as the symmetry of this particular system or this particular molecular orbital. So we have seen three types of overlapping: how s orbitals overlap to form sigma bonding, sigma anti-bonding; how pz orbital overlap to form pz bonding and pz anti-bonding; and how px, and similarly in the same way py will also overlap. So how px or py are going to overlap to form pi bonding and pi anti-bonding molecular orbitals. Now once you have understood these molecular orbital, there are certain things you should understand from the quantum mechanical point of view also. So this was all the visual representation, okay, how visually you can understand. Now the time is to understand about the quantum mechanical aspect. All right, so let's assume that we have a molecular orbital, okay, and that molecular orbital is represented as phi. So phi over here is showing you a molecular orbital. Okay, so it's a molecular orbital, and that is formed by the linear combination of two atomic orbitals, psi1 and psi2. So what are these psi1 and psi2? So these are atomic orbitals. Okay, these are atomic orbitals. So what we can understand from here, that two atoms are there, atom A or atom 1 and atom 2. So these are the two atoms, let's say atom 1 and this is atom number 2, or I would rather draw it here. So let's say I have two atoms, atom number 1 and atom number 2. These are the two atoms. We don't know that what type of wave function they have, whether sp or whatever orbital it has. Just we know that these two atoms are there, both of them have certain wave function. The wave function corresponding to one is psi1, the wave function corresponding to 2 is psi2. When they are going to do the when they are going to form the molecular orbital is given by your phi. So phi is representing the molecular orbital here. So when they are going to linearly combine, they form a molecular orbital phi. Now this C1 and C2 comes as the coefficients of these two wave functions, like phi1 and phi2 will have certain coefficients C1 and C2. Now what this C1 and C2 tells you? So the overall wave function or overall molecular orbital which will be formed by the linear combination of two atomic orbitals can be represented in this form, in the general form, that phi is equals to C1 phi1 plus phi is equals to C1 psi1 plus C2 psi2. So just understand this, that wherever you will be getting linear combination of atomic orbital, the molecular orbital will be represented like this. So here two atoms have linearly combined. It may be possible that there are more than three atoms which linearly combine. So in that case, we will have more wave functions there. If three will be there, so C1 phi1 plus C2 phi2 plus C3 phi3. Okay, that's how it will be. So C1, C2 and C3 or C1, C2 over here are basically the coefficients. So what these coefficients tell you? So this coefficient, the mod of the square of coefficients tells you about the probability of finding electron in that particular orbital or that particular wave function. So what is the probability that, see, these two atoms are going to share electrons to form the bond between them. Obviously this atom A first and atom number 2 both are going to share electron to form the bond between them. Now what is going to happen, that what is the probability? Now it depends upon the atoms, that how this electron is going to get distributed among them, depending upon the dipole moment of the atoms or depending upon the dipole moment of the molecule, or Yeah, there are different factors. So let's say that we have a carbon dioxide molecule, okay, CO molecule. So in that case, your atom number 1 becomes your carbon, atom number 2 becomes oxygen. So if they are going to form a covalent bond, the electron will be more towards your oxygen atom, okay. So electrons will be more towards oxygen atom because of more electronegativity of the oxygen atom. So in that case, probability of finding electron in the psi2, that means the wave function corresponding to oxygen, will be high as compared to the like probability of finding electron towards carbon side, okay. So in that case, what will happen, that C2 square will be greater than C1 square. So what does it tells you, that the probability of finding electron around the second atom is more as compared to the probability of finding electron around the first atom, okay. So this tells about the dipole moment of the molecule and all. So yeah, C1 square and C2 square gives you a very important property. That means it tells you about the probability of finding electron around that particular like atom. Now there will be different questions, I will take them and I will show you. They were asked in GATE exam and how to solve them based upon the same concept, okay. So make this thing very clear, that if you are given with a molecular orbital where you have linear combination of different atomic orbitals, so the coefficient of those atomic orbitals, square of coefficient of those atomic orbitals, tells you about the probability of finding electron around that particular atomic orbital. All right. Now once you have understood this thing, the next thing is even more interesting, and that is your overlap integral. Now what does this overlap integral means? It means in the starting, as I told you, that the atomic orbitals overlap to form bonding and anti-bonding orbital. Let's look upon this example. So these were the wave functions which overlap and they formed these bonding and anti-bonding molecular orbital. Now the question is that how much do they overlap? Okay, how much overlapping is between these two atoms? So that overlapping, that amount of overlapping will be discussed by the overlap integral. So overlap integral tells you that whether there is overlapping happening or not happening. For example, for the bonding molecular orbital, you can see that yes, there is a overlapping happening, like they are actually going to overlap. So this is actually how it is going to be, and then the overall wave function will look something like this, right? That's what you have seen here. So there have been certain amount of overlapping which has happened. So how much overlapping has happened, that will tell you that how much strongly they have bound or how much close those atoms are. So these all parameters or these all values or these all like properties you are going to get from the overlap integral. So overlap integral becomes a very important concept once again. So the overlap integral is denoted by S, and S is equals to integral of psi1 psi2 star deta, where psi1 and psi2 belongs to the wave function of the two atoms as we have discussed. So if there are two atoms, atom number 1 and atom number 2, so the wave function corresponding to this is psi1, corresponding to this is psi2. Now if they overlap, so how much they have overlapped, that will be calculated by the overlap integral, and this will be psi1 psi2 star deta, okay. If it is in one dimension, deta will become dx. If it is spherical, then deta will have different value. So it depends upon that. Now for a normalized wave function, if you are given with a normalized wave function, let's say this is how we have taken one more example. Like once again we have taken the similar example of the molecular orbital wave function. So phi is equals to c1 phi 1 plus c2 phi 2. So for that, overlap integral can be calculated from this formula, which says c1 square plus c2 square plus 2 c1 c2 s is equals to 0, where s is basically your overlap integral and c1 c2 are basically your like coefficients of your like atomic orbitals in the molecular wave function. So this much knowledge if you have, if you understand what the wave function is, how the atomic orbital overlaps, like what is going to be the overlap integral or what a overlap integral tells you about, what does the coefficient of the atomic orbital tells you in a molecular orbital. If you know this much, at least you can do one type of question from quantum mechanics, and this is going to be very useful if you are doing a question from IIT JAM, if you are doing a question from a CSIR net, or if you are doing a question from your GATE exam also. So in any competitive exam, this is the easiest type of question which can be asked based upon chemical bonding and coordination, chemical bonding and quantum chemistry collectively, okay. So you should be aware about it. If you are not aware about it, just let me know in the comment that yes, you got to know this from this particular video. All right, so let's take some questions now from the previous years of GATE exam. Let's try to solve them out and see how these concepts will be used to solve those questions. Alright guys, we'll start from this particular question which was asked in GATE 2008 exam, and the question says that the wave function of a diatomic molecule has the form, the wave function is given to you as psi is equals to 0.89 phi covalent, okay, and plus 0.45 phi ionic. Okay. Now it says that the chance that both the electron of the bond will be found on the same atom. So both the electrons of the bond will be found on the same atom in the 100 inspections of the molecule approximately. So they have tried to confuse you a little bit, but you have to stick to the concept. Okay. So you remember when there are two atoms A and B, and when a covalent bond is formed, so basically electrons are being shared with both of them. So if I draw the Lewis structure of a molecule AB, so what will happen, that A will have electron, B will have electron, so the Lewis dot structure is basically made like this. Okay, so these electrons are shared between both of them. But when an ionic bond is made, or when an ionic compound is made, let's say that B is more electronegative than A. So what happens, that A give its electrons to the B atom. Okay, so it gives its electron to the B atom, and that's how happens that A will have plus charge and B gains 2 electrons along with the negative charge. So that's how the ionic bond is made between them. So ionic bond happens, or ionic bond is made when both the electron stays on a single atom, and that's what is asked in the question. It says that the chance that both the electrons of the bond will be found on the same atom. So if both the atoms or both the electrons are being found on the same atom, so basically they are talking about the ionic bond. So you just have to look upon the ionic part of the wave function. Now they are asking the chance or the probability, right? Chance means probability. So how you will get the probability? So that is going to be the coefficient. Now since the coefficient is 0.45, and I told you that the probability, I'll just write down here that the probability basically tells you the square of this. Okay, so mod square of this. So just square this up, and if you square, you will get 0.2025. You can use your calculator because it's a gate exam. Now they are asking in the 100 inspection, that means you have to take it to the terms of 100, or you have to come multiply it with 100 to get in the form of 100 inspections. Okay, so 0.2025, just multiply it with 100 and you are going to get 20.25. That means the correct answer is option number B, which is around 20. So approximately the correct option comes out to be option number B. So see how simply the question was a little complicated, but how simply you have applied whatever you have studied to solve this question. You just need to know the basic idea of ionic and covalent bond. Let's go for the next question then. Okay, the next question here is pretty simple. This type of questions are generally done on a very simple concept. Okay, it says this was first of all asked in GATE 2020, that means very recently, and it says that among the following linear combination of atomic orbital, the correct representation of lowest unoccupied pi molecular orbital of butadiene. Now for this you need to know some basic understanding of butadiene first of all. Okay, so butadiene, what it is, this is basically your CH2 double bond CH, single bond CH and double bond CH2. This is your butadiene. There are 4 atoms. Basically we are just talking about the pi orbitals here because this talks about the pi molecular orbital. So there will be 4 atoms which contain pi orbitals. So you will have 4 molecular orbitals, 4 pi molecular orbitals. So those will be given as your psi1, psi2, psi3 and psi4. You can draw them, even the orbitals you can draw, but okay fine, we'll try to draw it. So basically what concept you have to apply is number of nodes. Okay, so if I write down the number of nodes here, so the number of node is 1 less than which orbital you are talking about. So psi1 will have 1 minus 1, that is 0 nodes. Psi2 will have 2 minus 1, that is 1 node. Psi3 will have 3 minus 1, that is 2 nodes, and psi4 will have 3 nodes. So if I draw the wave function, so this is how it will be. Okay, the 4 orbitals will be here. The shaded part is showing you the positive part, then unshaded is the negative part. So 0 nodes in this case. In this case you will have a single node, so that means it will be drawn something like this. Okay, the wave function will be something like this. For psi3 you have 2 nodes, so you can draw those 2 nodes like this. Okay, where those nodes are, I'll explain you that also. Okay, so in this case the node is here, in this case the nodes are in these 2 places. Psi4 will have 3 nodes, so that means 1, 2, 3 and 4 orbitals. So the nodes are here. Okay, this is how you will make, and it will have 1 node, 2 node and 3 node. Okay, so all the 3 nodes are here. Now once you have understood this much, it's pretty simple to approach the question. They are asking about the lowest unoccupied molecular orbital, so they are talking about LUMO. So you should know about HOMO and LUMO. So how many pi electrons are there? So 2 and 2, that means 4 pi electrons. So if I fill those pi electrons in these energy levels, so they will be filled according to the Hund's rule like this, making this psi2 as your HOMO because it is highest occupied molecular orbital, and your psi3 as your LUMO. Okay, now psi3 will be your LUMO, and how many node it has? It has 2 node. Now you have to look upon the options where you have 2 nodes present. Okay, so if you how to check out the nodes here, so just you have to see that how many times the sign is changing. In option number A, the sign is changing once, okay, from here to here once, then twice, and then again thrice. So how many nodes you have? 3 nodes in option number A. For option number B, you can see that sign is plus here. So plus to minus, sign has changed once. It has not changed yet, but it changed here. So there are 2 nodes here. 2 times the sign has changed from plus to minus. It remained minus, but here again from minus to plus. So 1, okay, 1 from here to here, and the other time from here to here. So 2 nodes. Option number C, see, it is plus, it is also plus. So no change. The only change it happened is just once. So just 1 node in this case. In option number D, since all of them are plus, so 0 nodes in this case. So you are talking about your LUMO. LUMO is going to be your psi3, that means 2 nodes. So 2 nodes is in option number B. Option B becomes your correct answer. So just by understanding the nodes and just by finding out the number of nodes, you can simply answer. You don't have to worry about the coefficients as well. Okay, so this is how you have to do this question. Alright, let's go for the next one then. Alright, so let's talk about this question which was asked in GATE 2012 exam. It says let phi xc and phi zc denote the wave function of 2px and 2pz orbital of carbon. Okay, so understand this. This phi xc denotes x orbital of carbon. This c is denoting carbon, x is denoting the x orbital. Like this is denoting the 2px orbital of carbon, and phi CZ is representing 2pz orbital of carbon. Okay, this Z is representing that it is 2pz, this C is representing that it belongs to carbon. Now if you take the other part, that is phi XO, so I can write it down as phi XO. This represent the 2px orbital of oxygen, and phi OZ represents 2pz orbital of oxygen. Now they are asking where C1 and C2 are the constants used for the linear combination. The carbon monoxide or the CO molecule is oriented along the z-axis. So CO molecule is oriented along the z-axis. Then according to the molecular orbital theory, the pi bonding molecular orbital have a wave function. So you have to just understand this, that if carbon monoxide is getting formed and if it is oriented along the z-axis, okay, this is, let's say, the z-axis. So where does the other axis goes? Okay, so let me just write down it properly. So, or shall I shall make the axis system to explain you. Okay, so let's say that the 3-axis system is like this. You have the z-axis, you have x-axis, and you have y-axis. So this is x-axis, this is z-axis. Now the carbon monoxide molecule is oriented along the z-axis. So carbon is there, and here you have oxygen. Okay, so this is how the carbon monoxide orbital is. Now which orbitals will be involved in the sigma bonding? So obviously those orbitals which are along the z-axis. So which orbitals will be involved in the sigma bonding? It's pretty simple to understand. The z orbital of carbon and the z orbital of oxygen will be involved in the sigma bonding. They will combine to form the sigma bond, right? Now which orbitals are going to be involved in the pi bonding? So obviously if I draw the orbitals here, so carbon pi orbitals will be like this, and oxygen also. The pi orbitals are always present perpendicular to the plane. So this is how the bonding is going to happen. So which orbitals will be involved in bonding? So the orbitals aligned along the z-axis, that means the orbitals aligned along the x-axis. So which orbitals are those? Those are your 2px and 2px of your oxygen. So how the bonding is going to get formed, or how so this is going to involve in the pi bonding. So what is going to be the answer? So the pi molecular orbital will be represented as, like if I call it as phi, let's say phi pi, that is phi bonding molecular orbital. Bonding, that means that has to be constructive overlapping, right? They are talking about pi bonding molecular orbital, not anti-bonding. So for bonding, the sign should be plus. Obviously, the answers are having plus signs, so you don't have to worry about. But if they confuse you with the sign, you should know that bonding molecular orbital will have a plus sign. Which orbitals will be there? So obviously C1 you will write down because that is a linear combination coefficient. So let's write down C1, and then which orbital? So phi x c, that means the x orbital of carbon, and plus C2 phi x z o, sorry, xo. So x orbital of your oxygen. So x orbital of carbon, x orbital of oxygen, both are going to linearly combine to form a pi bonding orbital. So that's how your option number D is correct. You just have to look upon the orientation of the atom, and you just have to see that which orbitals will be involved in bonding and which orbital will be involved in sigma bonding, which will be involved in pi bonding. If let's say the question, if the same question was for your sigma bonding, that which orbitals are going to be, or what is going to be the wave function of the sigma bonding molecular orbital. So tell me in the comment section that which option will be the answer, A, B, C or D, which would be the answer for sigma bonding. Okay, I want answer from you guys. So tell me the answer for that in the comment section below. Alright, let's take the next question then. Alright, let's do this numerical answer type question. This is a NAT answer type question asked in GATE 2017 based upon similar concept. It says that phi is a wave function, phi is equals to C phi 1. Okay, I'll write down here phi is equals to C, sorry, psi is equals to C phi 1 minus 1 upon under root 2, sorry, under root 3, and then you have phi 2. This is the wave function given. Represent a normalized molecular orbital constructed from two different atomic orbitals. Orbitals are your phi 1 and phi 2. These are two atomic orbitals. They form a orthonormal set. So what does that mean? What is an orthonormal set? So an orthonormal set means, orthonormal set, it means that if I multiply this like if I multiply these two wave function phi 1 with itself, okay, that means if I do phi 1 square, this is going to give me 1, and similarly if I do this phi 2 square, this is also going to give me 1. But if I multiply this phi 1 with phi 2, in that particular case I will get 0. Okay, so this is normalization, this is orthogonality. Both of them combined is called as orthonormal set. Okay, now one thing which you should understand, that for the orthonormal set, they will not overlap. Okay, the overlap integral is 0 for that. So for orthonormal set, overlap integral, okay, overlap integral is 0 because they cannot overlap. Okay, they, whenever they will overlap destructively. So there is no overlap integral. The value of S becomes 0 in that case for all orthonormal sets. Now same concept you have to apply. They are asking you about the value of C. So for any wave function, you know ki, like if I call it as C1 and if I call it as C2, so in that case your C1 square plus C2 square plus 2 C1 C2S should be equal to 1. And since this is forming an orthonormal set, so the value of S will become 0. So this particular part will vanish out. You will have C1 square plus C2 square is equals to 1. Just put the value of this. C1 has a value of C, so C square plus C2 has a value of like minus 1 by root 3. So minus 1 upon root 3 ka square, that should be 1. Just solve it. So your C square becomes 1 minus 1 square will be 1, root 3 square is 3. If you solve this out, C square becomes 3 minus 1, so that is 2 by 3. Okay, so C square becomes 2 by 3, or you can say that 0.677, 0.667. So C square becomes 0.667 or 67. Now C will be equal to under root, it can be plus minus both. Okay, so they are asking about the value of mod of that, so obviously you just have to take the positive value. In the question they have asked about the mod of that, so under root 0.667. now do this, like use your calculator to solve it, and that's what will be your correct answer for this question. So when you will solve this using your calculator, you are going to get value of 0.81. okay, so your correct answer becomes 0.81. this is going to be the value of your C, mod C. Okay, that is how this question has to be done. Alright, I think this is much clear to you. Let's go for the next one then. Alright, this is the last question for this video. It says that in the molecule XY, let's say psi X and psi Y denote normalized atomic orbitals of atoms x and y respectively. A normalized molecular orbital xy is given as psi plus, and psi plus is given to you as 0.56. In the bracket you have psi x and plus psi y. They are asking the value of overlap integral. Okay, they are asking the value of overlap integral. So let's try to solve this. What you have to do, first of all, multiply inside and make it in the standard form. So psi plus will be equal to 0.56 psi x plus 0.56 psi y. Now if you compare it with the standard equation which we were using, was like psi is equals to c1, let's say this is phi, so phi is equals to c1 psi 1 plus c2 psi 2. Now with that you can say simply that your value of c1 is 0.56 and the value of c2 is 0.56 again. If you use the formula to calculate the overlap integral, which is mod c1 square plus c2 square plus 2 c1 c2s, it is equals to 1. Let's put the value, so 0.56 ka square plus 0.56 ka square plus 2 times of 0.56, 0.56, and s is equals to 1. Now you have to find out the value of s. So you can use your calculator to do the calculation part and you will get your answer. So I'll just quickly do it and let you know. So when you will solve this whole thing, you will be just getting s is equals to 0.59. Okay, so the overlap integral comes out 0.59 as the answer. Okay, so that's how you have to do. You can use your calculator to solve this particular part because it's a GATE exam question. So obviously you are allowed with the calculator. So I hope this particular linear combination of atomic orbital you have understood, and I have taken 5 questions and 5 different types of questions so that you get to know that how to solve or how to apply that concept to solve questions. All right. Well, that's it all for this particular video, guys. I hope whatever we have studied, whatever we have understood in this video will help you in the upcoming exam and you guys understood this concept well. If you understood this concept and if you like the video, give it a like, and if you have not subscribed to the channel, do subscribe to the channel. And you can also follow us on different social media platforms. We are available on Facebook as well as we are available on Instagram. So you can follow our page, that name is All About Chemistry. The channel link or the channel handle is @chemoholic. So you can search it out on Facebook as well as on Instagram, and you can join us over there for interacting with us more. All right, so that's all from my side, guys. Thank you so much for watching and have a great day. Bye bye.